Our next speaker is Dr. Mengistu Goa from University of Botswana, and the title of his talk is Fixed Point Approach to Constrained Convex Minimization Problems and Equilibrium Problems. So Dr. Mengistu, you can continue.
Thank you, Chairman. Thank you, Dr. Professor Mirar, for giving us this opportunity to present our works to the public. I think this platform is one of the important platforms we have. My talk is on fixed point approach to constrained convex minimization problems and equilibrium problems. It is just continuation of those four presenters, especially one of the presenter, Dr. Solomon, was my student in MSc as well as in PhD. I supervised him in both MSc and PhD, so he presented at a bit already higher topic to you. You saw it. It is part of his PhD dissertation. Now, thank you, Professor Abbas. You gave me even a good opportunity because it is a good platform. Now, I cannot make too much effort to explain each and everything because already Professor Abbas mentioned many of the things, and I will focus on some of the applications. Now, my presentation is just simply I shared abstracts, then motivation and introduction, iterative algorithms, concluding remarks, and the bibliography part. And in this already presentation, we discussed fixed point approach to a constrained convex minimization problem and a generalized equilibrium problem. Also, we explore some iterative schemes in approximating a common solution of a constrained convex minimization problem, an equilibrium problem, and a fixed point problem of a nonlinear mapping in the literature. Finally, we review the iterative schemes in the literature compared to the well-known gradient projection algorithm. Saying that these are already the ones Professor Abbas clearly mentioned them, but just for sake of completeness, these are the terminologies we have. I am focusing only on real Hilbert space with the inner product and the induced norm as usual. And the C is a non-empty closed convex subset of H, which is very nice already space we have. One of the nicest spaces already in functional analysis is closed convex non-empty subsets of Hilbert spaces. They are weakly compact and so on and so forth. So they are very nice ones. And we call already mappings. We have what we call L-Lipschitz mapping, contraction mapping, non-expansive mappings, Fermi non-expansive, alpha averaged mapping definitions are there. They are already common ones for almost as a background because they already, especially those, the Broad, the Schroeder, the Banach, most of them are just on these functions. So in this kind of operate self-mappings, therefore, these are the types of mappings I'm going to engage with. And the other part is because most of the time equilibrium problems are related to monotonicity. Therefore, monotone mapping definition, just as for sake of completeness, I put it here as a definition. So a mapping is monotone if just in the, it is not too much different from the monotonicity or the decreasing mapping in one variable case. So it is almost a product here. So that's greater than or equal to 0, then we call it is monotone. V inverse is strongly monotone as well, which is much stronger than the monotonicity. And these operators are practically applicable in optimization problems, traffic assignment problems, equilibrium problems, radiation therapy, and so on. I think Dr. Solomon mentioned in detail about the applications of those things generally equilibrium problems because equilibrium problems are attached to these ones. I think this someone might simply refer to the listed citations here to get already about or to get hints about the monotone mappings. Now, the three key problems I want to focus in this presentation are the first one, the fixed point problem. So I don't know, I have to add anything more or not. Professor Abbas mentioned them all, including their pictures. So of those people, but I add some more. Brouwer theorem is there, Schroeder's theorem. Both of them are for non-expansive mappings, especially for Brouwer one is for continuous functions, as Professor mentioned. Schroeder theorems already accept changing the domain to be compact subset of infinite dimensional spaces. They are almost the same theorems. Then the 1920 Banach contraction mapping theorem, which he tried to categorize those mappings. So they are also important group. The other already next to, I think in my view, next group of people who did a lot for, contributed a lot for uh, this field are William Earth Kirk from Iowa State University, and Gohide from, I think, French mathematician, and a broader also American mathematician. I think Professor have shown you the picture of broader as well. So their theorems for non-expansive map is around 1965 to 1967. So then I think 60 years ago, or 60 to 60 years ago, these three independently proved existence theorems and approximations for non-expansive mappings. The other extension we have is Goebel and Kirk in 1972. They extended already the same person, Professor Kirk, I think, extended it to asymptotically non-expansive mappings, which was also one of uh, the most already cited results in literature, I can say, in fixed point theory, because the extension of mappings from contraction to non-expansive to asymptotically, it is a difficult task, but they did it. So we have many theoretical background, especially on the fixed point problem. Therefore, existence theorems, as Professor mentioned, Banach contraction principle, why it is widely applicable, because it's not only existence and the uniqueness, even we are able to construct a sequence of points that converges to the exact point or the fixed point of the function. So that's already the beauty of Banach contraction. In the same way, William Kirk in 1965, Professor Goide as well, and the Professor Broder, both of them did for non-expansive mappings. So I think that's why we have the Picard iteration failed to converge. Then they come up with MAN iteration, which was introduced in 1950-55 by Kranowski as well. And then we have also, I think those Ishikawa iteration, which was introduced in 1972, around 1976, sorry. So those are one already the important algorithms we have. The picture of fixed point theory just comes to the surface by using, that means we have no constructive method. We might prove the existence, uniqueness, but the challenge we have, especially in applied areas, is to exactly approximate the solution. So that's why we have this. I think I recognize these people for what they did. The second group is the usual problem, the constraint convex minimization problem. For especially, I am taking you to a most simplest group of functions, those functions which are convex and continuously differentiable. So we have the minimization problem is here. This is a common problem mathematically. Then people try to check first existence, second, and they used already this algorithm, what you call the gradient projection algorithm. it is most widely applicable one for uh, minimization problems in optimization. So this is
Dr.
what we
Mangistu,
call,
can you make your video on?
it is on.
I don't
It's
know.
not
Yeah, it
on.
is on, but we cannot see you. No problem.
It's on.
Okay.
Maybe you can check the
Okay.
camera at the
Yeah.
top in your laptop.
Yes, it is on.
Yeah, we see it. It is on, but we are not able to see.
Okay.
Yeah, continue.
Maybe you
Okay.
can remove
Use
the
video.
lead for the camera.
Is it visible now?
No, it's not visible since you
Okay.
started. Yeah.
Okay. Now the third problem is equilibrium problem, which was in 1994. Bloom and Otele, they introduced already this equilibrium problem. Nowadays, many of already the problems we have, like variational inequality problems, optimization problems, most of them are changed into equilibrium problems. So they are helpful in, especially in image restoration, computer tomography, radiation therapy, treatment planning, economics, optimization, and so on. I think my student even have shown you the different approaches already where we can apply the fixed point, already the equilibrium problem is there. Now, but monotonicity is the key already issue which is attached to equilibrium problems. Therefore, monotonicity, the bifunction involved here, we need already the monotonicity assumption on it. So that's where it lies. But some researchers, generally, many researchers consider a generalized form of the equilibrium problem by introducing additional operator A here, and then pi is bifunctions, and pi zy plus az inner product az y minus z is greater than or equal to 0 for all y element of C. So this is also generalized form of equilibrium problem. I think interested ones may just refer to, I listed some of the main ones here. And now I will just how researchers just converted the minimization problems and the equilibrium problems to fixed point problem. So this is the first one. In 2010, Professor H.K. Shu published already in inverse problems, and he proved this one. If we are sure that our function g is a convex function whose gradient is L Lipschitzian with L greater than 0, and assume that the constraint convex minimization problem is consistent, means it has a solution, then the gradient is 1 over Lism. That means it is inverse strongly monotone. For lambda greater than 0, the mapping is averaged mapping, and the composite, that means where lambda is taken from this one, is averaged, where 0 is less than lambda, lambda is less than 2 over L. So here, the key part is the fourth one, which changes the whole minimization problem to fixed point problem. So this is the main result of that paper in 2010. X star element of C solves the minimization problem to if and only if for any fixed positive number lambda, X star solves the fixed point equation here. So that means already our minimization problem is converted to fixed point problem. Next is this theorem, already this definition on the that means on a given bifunction, we say this a given bifunction satisfies condition A if the following four conditions hold. So the first one is pi xx is equal to 0. Pi is monotone. That means the sum is less than or equal to 0. But some even researchers relaxed these conditions as well. In the recent future, many researchers also relaxed these conditions. And for each x, y, z element of C, this holds true. That means in the first variable, it is semi-continuity. That means semi-continuity is shown here. It is upper semi-continuous. And for on second variable, it is weakly lower semi-continuous. So these conditions, the four conditions, we call them condition A, as Dr. Solomon also mentioned them. Now, this is the theorem which was published, I think, in 2016 or 2015, and it was changing. It is changing the whole thing from equilibrium problem to fixed point problem. So if our bifunction satisfies condition A, then this operator is single valued. QR is firmly non-expansive. That means this satisfies this condition. And fixed point of QR is equal to EP of phi. That's the solution of equilibrium problem. Therefore, and the set EP pi is closed and convex. Therefore, this is the one that translates equilibrium problem to fixed point problem. So this is what we have. Then have the following remark. Now it follows from theorem 2 and the theorem 4 that both problem 2 and the problem 3 are also fixed point problems now, because we have changed them into fixed point problems. Therefore, so we are left with the question of identifying key properties for the operators obtained by changing these problems to fixed point problems. Therefore, how important is Professor Abbas' presentation? Because it helps us to identify the fixed point questions we have. Advantage of having a fixed point problem, it's already easier to solve. When we have many theories developed also, then for applied areas, it makes things very easy to use the theory. Therefore, that's one advantage, already advantage of fixed point. Now, just this part is my main result with two of my students, which we published in 2025 April and 2026 February. So we assumed all the conditions here, our mapping and so on, but it is the conditions imposed are B1, B2, B3, B5, and even on these conditions, Philip Tang and Pan Panning introduced an iterative scheme of this form, which already for where A is strongly positive bound linear operator on H. It is linear operator. S is non-expansive self-mapping, such that this set is non-empty. So alpha n's are taken, they proved strong convergence of this algorithm to the solution, equilibrium problem, as well as the fixed point of S and solution of the equilibrium problem. In 2020, Mariam Yazdi introduced the following explicit composite iterative method, just this iterative method, to approximate equilibrium problem here and the fixed point, that means minimization problem here. These TNs are associated to the mapping G, which we are going to already find the minimization problem. So these two combined, that means it is to solve the constrained convex minimization problem and the generalized equilibrium problem. If the system has two such problems, then what's the common solution for them? So they introduced this iterative algorithm and proved the strong convergence to the common solution, a common solution of the two problems. In 2024, the same group of Mariam Yazidi and the Sabab, they proposed the two-layer iteration process here. Still, they have already alpha strongly quasi non-expansive mapping, such that I minus t is demi-close at 0. So they use this mapping, fixed point for this one. This is the solution for equilibrium problem and the fixed point problem combined, the two combined. That means they considered two problems, fixed point problem and equilibrium problem, and they proposed this algorithm. In 2025, Sangago et al., Sangago, Dana, and Kasu, we try to solve the three together, the three problems. That means we propose viscosity iterative algorithm to approximate a common solution of the three problems: the constrained convex minimization problem, a generalized equilibrium problem, and the fixed point problem of directly non-expansive mapping. But this mapping, directly non-expansive mapping, is a bit strange than the non-expansive mapping, or it is above the Fermi non-expansive mapping, but below the class of non-expansive mappings. So we introduced this algorithm and proved strong convergency. Here, fixed point group. The second part is for minimization. It is related to minimization problem. And the first part is equilibrium problem. So the common solution for the three problems is approximated by this algorithm. And we proved strong convergency by imposing some conditions on the parameters. I think in the same pattern, with my PhD candidate, still it is with my PhD candidate, Mr. Ramatavele, Sangago, and Tufa, we try to introduce a mixed man-type viscosity approximation just to approximate solution for the three problems. So this is, I think, the algorithm we proposed, and we try to prove it. It converges strongly to a common solution of the three with the assumptions on the parameters in this way. So that's what I have. Then the open questions are, as usual, rate of convergence. We haven't already finished the work of the rate of convergence of these iterative algorithms are not well investigated. In comparison to the existing algorithms such as Picard, MAN, or Ishoka and their extensions, the challenge of coding these algorithms have not been well investigated. In the last two results, we have the new class of mappings called directed non-expansive mapping is introduced. Still, it was shown that class of mappings between the class of Fermi non-expansive and a class of non-expansive mapping, but we haven't completed the characterization of this class of mappings. Is still an open problem. Therefore, someone can work on them who are interested. These are already some of my citations. Thank you, the audience, for your attention. Thank you, Chairman.
Thank you so much, Dr. Mangustugoa, for the great presentation. And let us thank our speaker.
Yeah, you ask one question, please.